The equations of continuity. So let's consider a fluid's flow in a non-uniform pipe. In this case, the fluid is flowing through a pipe whose size is not constant, meaning the diameter or cross-sectional area of the pipe changes along its length. As we mentioned previously, in a steady-state flow, the fluid's velocity at different points does not change over time. Also, the particles in the fluid follow a path which usually refer as streamlines, which are imaginary lines that represent the fluid's flow. Each particles along a streamline move at the same speed as other particles on that line. Let's say in this time delta t, the fluid entering the pipe at the top at distance of delta x1. This distance is calculated using the formula delta x1 equal to v1 delta t, where v1 is the velocity and delta t is time. To recap, what is the equations of velocity? So the equations of velocity is v1 equal to the displacement divided by the delta t. Here we assume that all particles share the average speed. The mass of the fluid in a particular section of the pipe can be represented as m1, and the mass can be calculated according to the equation m equal to rho ax. Here rho is the density of the fluid at that location, a is the area, and is the distance of which the fluids travel. This equation essentially says that the mass in these sections of the pipe is the product of the fluid's density, the cross-sectional area, and the distance of the fluid moved in during the time delta t. We can simplify the mass formula by substituting delta x1 equal to v1 delta t into the mass formula, and we get delta m equal to rho a v and t. The formula in this step 3 shows that the mass of fluid moving through these sections of the pipe in the time delta t depends on the fluid density, the cross-sectional area of the pipe, and the fluid speed. Similarly, the fluids that move out at the lower end of the pipe in the same time interval t has a mass of m2 rho a v t. Since mass is conserved and the flow is steady, the mass at point AB and CD at delta t must be equal. Therefore, we can say that m1 equal to m2. Therefore, we can rearrange the equations to be in this form here, where rho 1 a1 v1 delta t equal to rho 2 a2 v2 delta t. In this step 6, for the case of an incompressible fluid, the fluid density of rho 1 and rho 2 should be equal, and the delta t is the same. Therefore, we can rewrite the equations as a1 v1 equal to a2 v2, where a represents area and v represents velocity of the fluid. The equation a1 v1 equal to a2 v2 involves two quantities, a which represent the cross-sectional area and v which represent the velocity of the fluid. To understand the unit of a1 v1, let's break down the unit of each component. The unit of area in terms of SI units is typically in m square. The unit of velocity is meter per second in the SI unit. When we multiply area by velocity, the resulting unit is cubic meter per second. In this form, we can say that AV describes the volume of fluid passing through a given cross-sectional area per unit of time. The equation AV also known as flow rate. This is another visualization of the equations of continuity. In this case, the volume rate that through A1 must be equal to the rate through A2.